Hello. Welcome to all of my combo lords out there. Sorry it took me a moment to connect today and that I started at around my 10:30 instead of my 10. I have a lot going on this wild week since it's the last week of grade -1. And I do have some other stuff coming out today as well. The footage coming out today will be the next part of my answer videos for the final exam questions I designed, which will be covering the sector about different bases. So stay tuned later today for a bonus video as well of different sorts of numerical based question I designed and the problem solving tricks you'd use to get to those. Sort of a refresher on some of the main things we've covered about bases so far in the form of questions I'll answer. And to anybody joining me for this video, we do have some fun math planned for this as well. Now, part of today's stream, I was just going to chat about some of the new transitions coming, some of which are hiding behind this tent that I have set up once again, because it is my last chance to have the tent here. There's going to be one or two more rains where I'm going to have to remove the tent, and then we will have a new desk and such clogging up this space. And behind there, some of the hidden secrets involve my lab coat, more demolished than ever. And yes, I'm not wearing either the more demolished lab coat nor the grade -2 lab coat. This week we are in between lab coats. However, we do still have some whiteboards available here, which I will grab because in this video, I'm going to need to draw some modular tables. Apart from chatting about some of these things going on, which you can visually see some of them as well. For those who did not see the last stream, I did cut the rest of my hair to catch up with the other half, although I cut it myself, so it's probably pretty messy. Probably needs some fixing. But what we're going to look at today on whiteboards, in addition to that stuff, is the 4th edition of what I was calling Modular Mondays. And we looked at the number of the mod in each of those previous ones. Although in Mod 1, it was more the lack of a Mod 1 we looked at. In Mod 2, and we could do things with Mod 1, not a complete lack of it, but like with bases, mods often have their full powers and their full time that you discuss them flourish and begin at 2. Base 2 is really the first of the bases that follow the same rules you're used to. Tally marks are not base 1 unless you start describing a bijective base and slightly different definition. Mod 2 we saw next is very similar to binary and has the patterns of even and odd numbers. Mod 3 had the patterns of what I called threeven and two types of throd numbers, post-threeven and pre-threeven throds. So what would Mod 4 be? Well, some people, when I first started saying these terms in my videos, said we need a fourven. That's not exactly true. While we might need to say feven for a multiple of 5 at some point, I often just say multiple of 5 because, I'm focused on threeven getting into a dictionary before we sink our teeth into feven. But, in fact, feven things are overrated by our base 10 system. They have enough credit. But 4, in between there, doesn't need to have a name based on 4-ness. These mods have their structure built up in a sort of multiplicative way. And with 4, funny enough, whether we said we were adding or multiplying, it's sort of built from a set of 2's. In this case, the way it's built from a set of 2's will more so be the 2 times 2 equals 4 leading here. But the 2 plus 2 does also equal 4. So we're going to draw some Mod 4 tables. As far as the comments right now, I will have the comments pulled up, so feel free to leave comments if you have questions at any point, but do remember I'll probably only respond to them every 10 minutes or so. I will answer one right here. Someone asked, what is Google? So let's get a whiteboard for that. So why don't I talk about Google much? It's a very large number, so one of the reasons that one wouldn't need to talk about it would be you're not going to encounter Google in your actual physical world unless I mean, we can debate about micro scales of things, but you're not going to count a physical Google in front of your eyes at any point. It's a very large number. But where's a pen? Google's worth mentioning. It gets a nickname, however, it's a bit overrated by our base 10 system. It's a very 10-based number, so it's easy to describe or think about in our base, but it doesn't make it a fundamental big number necessarily. So Google is basically just 10 to the power of 100. However, a more fun way to write it is that 10 squared is 100, so we could break it down even more. 10 to the power of 10 to the power of 2, because this bit happens first. But we'll write it the more common way, which is 10 to the power of 100, which means a 1. Since 10 to the power of 1 has 1 0, 10 to the power of 2 has 2 zeros, you can imagine that this, and yeah, the pen is not great, just imagine it says 10 to 100 really clear, would mean 1 with 100 zeros. And so that's the way people describe it, 1 with 100 zeros. It is mostly popularized by its friend Googleplex, and Googleplex is 10 to the power of Google. 10 with Google amount of zeros. So you could just say Googleplex is 10 to the power of that. Now, these are really big numbers, you know, they're bigger than anything you'll observe physically with your eyes in the world. However, I don't think they're necessarily the most fundamental big numbers. We could whip up a large factorial that might be more fundamental. We could look for a highly composite number in that range, or a superior highly composite number in that range. And we could even just make simple tetration towers. Like, we could say, what is 5 to the power of 5 to the power of 5 with 5 5s in the stack? That's sort of like more fundamental and neat looking than that. And so, okay. And so, with different stacks of number, I think you can make things using tetration, using factorials, other things using the families similar to tetration. There are these things called fast-growing hierarchies. There's a popular one called Graham's number, although that to me is a little overrated as well. It emerged in this one upper bound for something in a proof that quickly was shortened to a different number. But there are fundamental big numbers, of course, like someone says, not close to infinity. And it isn't, no number that's finite will be close to infinity. So when you're talking about big numbers, it's all comparative. You can make an argument that no number is big out of the finite numbers, but then you'd say, well, it's useful to have a term for the ones that are, you know, many digits or hard to express amount of size. And so then we would come up with a synonym for the word big. So you end up describing them as large, but, you know, that's only because we need a word for them. There's another definition of large under which no finite number is large. But then again, you could say no finite number is small, because we could take the reciprocals of any of these, 1 divided by any of these. So we got a fan of the fast-growing hierarchies in the comments, and we will cover those more in some future episode. One of the ones that I do think is pretty neat that some people mention when they mention stuff like Graham's number that's pretty big is this one called Tree 3. That one is different than the fast-growing hierarchies, but it is very similar in terms of it is fast growing and very fast, in that tree 1 and 2 are tiny and tree 3 is like, you know, way beyond Googleplex. And someone's saying they saw a question about an arithmetic progression and the solution was Google, and so that's why they had the question. And yeah, no problem. It's worth discussing comments that may not come up in a video that much in the streams whenever I have the chance, because often you'll hear me be like, Here's a topic I'll tell you a little about in the stream, but I'm probably going to dedicate a whole episode to this later because I have tons of cool notes about it. In this case, I'm probably not going to dedicate an episode to Google. Google is not that remarkable outside our base 10 system. You know, it's like, why not 6 to the power of 6 to the power of 36? Why not that? You know? What's different about that than Google? They're both built from a semi-prime in the same structure. Google gets a little too much credit. And believe that's all of the questions. So I'm going to find a better pen so we can whip up some modular tables. Now, to anybody who knew where I was going with this, based on, I guess it's spoiled in the title a bit, but I was mentioning how we don't need to say Forvin. And why is that? Let's see, where's a good pen? Okay, hopefully this one does the trick. No. Okay. Alright, I'm not going to show you folks all of the surprises from the new grade, but I will note this is just one of several new clocks. Now, oh man, should have restocked my pens too. Alright, I'm going to have to run inside and grab a pen from in there because I know I have ones in there that work. Okay, no, this one maybe is good enough. No. It starts out strong and then... Okay. I'm going to run inside and grab a pen in a minute. First, we'll just note the core aspect of our concept, which is we don't need to say Forvin, because since these modular tables are similar to multiplication patterns, we're going to be able to call those doubly even. And multiples of 4 in general can be called doubly even numbers, because an even number, under some ways of describing it, is a number that is an integer that can be split in half and get another integer. So doubly even would imply I can take an integer, split it in half, and then split it in half again and get an integer. And it's true that it's actually a mathematical term, doubly even. Singly even is even used as well to mean numbers that are divisible by 2 but not by 4. Now, doubly evens are usually the furthest the terminology goes, but there's no reason to stop there. We can call multiples of 8 triply even. We can call multiples of 16 quadruply even. We can call multiples of 6 threeven evens. Multiples of 12 are the numbers that are threeven and doubly even. So there's a lot of combos or doubling or tripling up of these terms that cover a lot of our nicknames right away. So remember that when we say even, it means multiple of 2 might be a multiple of 4 or 8. We didn't give enough data, so it means that it can be divided by 2 at least once if we say even. If we say doubly even, we mean it can be divided by 2 at least twice. And if we say triply, at least 3 times. And if we say singly even, that does mean that it's divisible by 2 only once. Now, if you want to be like, what if I want to describe a number that's divisible by something that's doubly even but not triply even? Well, I mean, I just described it, so you could use words like that. But in mathematical terms, you can call that the 2 order of the number. And what this starts getting toward is a metric called the p-adic numbers. P, the letter, representative of primes often, although in this case, the p-adic has... it's a whole rabbit hole to explain. but it's a relationship that numbers have related to sharing divisibility of high powers of something. And so eventually, when we do an episode about the p-adic number structure, or structures, because you could have the 2-adic, the 3-adic, or other ones, we will see that when I'm explaining the 2-adic metric, we will use terms like singly and doubly even to try and lead ourselves into the denser math stuff. Someone's wondering what an even Steven number is. Good question. Maybe somebody named Steven needs to discover a really cool integer sequence that mostly is made up of odd numbers but has a few evens sprinkled in. Now, someone's wondering if there's 0e evens or 1e evens. Well, if you mean like at least once even, kind of like doubly meant at least twice, that's just the term even. So even means at least once even. And a term for 0e evens, if you mean like not divisible by 2, well, if we're talking about integers only, those are the odds, because the integers all come in either even or odd. So to get technical, we can write these in names of modular arithmetic, or a way that helps some people digest it as well is to say an even number is made up of 2k for some whole number k, and an odd number is made up of 2k plus 1 for some whole number k. So then we could similarly go further to use language like that to describe what it means to be singly even, what it means to be doubly even and stuff. I'm going to run inside and grab a working pen that's actually dark here. And then while I'm there, listen to the birds for one, look for the squirrels, and leave a comment if you think you know any mathematical ways we could define a singly even number. A number that's divisible by 2 but not 4. How could we describe that mathematically? There's 2 ways I have in mind. So I'll be back in a moment. All right, that's a nice bird. Hope you folks have been appreciating the birds. And, and yes, we have one of the ways that we could phrase it written in the comments by Mathematique Morse, which is we could write, oh, please work. Okay, we're going purple today. That's the color that works. We can write 4k plus 2 is singly even. We can also call them numbers that are congruent to 2 mod 4. We can also call the doubly evens 4k or congruent to 0 mod 4 and describe our doubly evens. And remember that the doubly could be triply or might not. Both the nicknames and the terms here are ambiguous as to whether it's divisible by 8. We just know it's for sure divisible by 4. Now, here we can draw some charts here that's going to help us identify some patterns in this mod. And one moment. And someone asked, why not 4k minus 2? That would work as well. Addition just makes the math a little easier if you ever multiply these out to find patterns. So it's just a little easier to go with plus 2, but you could do minus 2. You could even call odd numbers 2k minus 1 is, not that uncommon. So sort of a choice. However, that's similar to the fact that we could call these congruent to negative 2 mod 4, which is also true, but it's sort of like why put the negative sign unless there's a reason. If I'm saying it's congruent to negative 2 means the same as congruent to 2 in this mod. So similarly, odds and evens, odds are congruent to 1 mod 2, and so we could call them congruent to negative 1 mod 2, but it's a little unnecessary. So here, if we look at all the types, we can make a chart. And let's see. To wipe this off, I will use the good old lab coat, which will give a small little preview of... Don't fall. Don't fall. Okay. So, wiping it off with the lab coat will give a little preview of why the lab coat's not being worn right now. It is gone through its most intense damage, as you'll see in the finale episode coming out on the Combo Class channel sometime later this week during March, probably right near the end of March. And there's a new fresh lab coat for grade -2 that I will begin wearing in not too long. This one now I can lend to any visitors who come by the classroom. So if I ever have some, professional mathematician pop by, I'll be like, hey, you need this to protect yourself from the elements? All right. So, what are some notable bits of data we could try and gather about these numbers? Well, one of the first things I always like to do is make an addition table and multiplication table for the given mod, because those tables will conduct a lot of patterns for us. And so, let's get this as clear as possible, and first start with our addition table. Our values we can be congruent to in this mod are 0 through 3, because multiples of 4 are called 0. They have no remainder after division by 4, and similarly they end in the digit 0 in base 4. So here we'll make a little addition table, and we'll note that 0 doesn't change anything. 1 plus 3 gets us back to 0. And we sort of have this like looping around structure where there's some cool ways you could look at it, because here it's like 0, 1, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1, 3, 0, 1, 2. But there's also a symmetry on it where it's like 1, 1, 2, 3, 0, 1, 2. So this represents our modular addition patterns, like what happens when I add two singly evens? I get a doubly even. What happens when I add these different types of in-between number? Now, as for nicknames, I still haven't settled on my favorite nickname to give the in-between ones, because these are doubly even, these are singly even, but with the threeven numbers, the two types of throd I was calling a post-threeven and pre-threeven throd. It's not as elegant of a nickname to call it a pre-doubly even odd, post-doubly even odd. So I'm going to think at some point of what's a good nickname for these. I'll let you folks know once I've got my full list of idealized nicknames. But for now, we may give them that full title of referring to these as, this one could either be called post-doubly even or pre-singly even. And this one could be called post-singly even or pre-doubly even. But we can also note just their congruence class in the mod, which is there are 4 congruence classes for integers in this mod, 0, 1, 2, and 3. So I'll get to some more questions in a minute. First, I got to whip up our even more important table, our multiplication table. And I don't know if I would say more important, but probably has more often the awesome patterns that we're going to need to analyze will be in the multiplication tables. So in our multiplication table, we can see 0 times anything is 0. What does that tell us in terms of nicknames? That tells us that anytime you multiply a doubly even number by any other whole number, you get another doubly even. Now if we multiply 1 by these, we get the number itself. Same with this direction because of the symmetry. What's that sound? Is that a squirrel or something? Huh. But stuff falling from the tree, but it's probably from a squirrel or someone running around. Huh. So, with our multiplication table, we can see that 2 times those alternates, and 3 times 3 would be 9. In that mod, it's 1. So, this, if you look at the nicknames, tells us a bunch of patterns, like how one of these that are odds, 1s and 3s are the 2 types of odd here, have their own type of pattern of what they multiply to get. And a singly even multiplied by another singly even or doubly even gets a doubly even, but multiplied by an odd just remains a singly even, and so on. But what other cool patterns can we find here? Well, we could say things like, how are the possible ways we could get a given type of number? There are a lot of 0s and 2s, well, a bunch of 0s and a decent amount of 2s on here. There are less 3s and 1s on here. So maybe we might think, when can I get the different types of odd? Well, to get the congruent to 3 odd, and what we'll call them right now as a nickname, that's one nickname I sometimes think of them as, is, this may not be the final nickname I use in episodes, but we'll call these ones just for a minute to keep it nice and digestible, the early odds and the late odds. So we'll say an early odd is one that comes right after a doubly even, and a late odd comes after a singly even there. Which might sound backwards, but that's the order they appear in when we're coming from 0. So the only ways to get the 3s, the late odds, are to multiply a late odd by an early odd. How can I get an early odd? Well, I can multiply an early odd by itself or a late odd by itself. So some of these patterns give us patterns in little tables that are expanded from the mod 2 one we saw before, but we get a little extra room to have some interesting stuff. If I just made the mod 2 multiplication table, it would end up just looking like the corner of this, because there's not enough room to wrap around to anything different. So the multiplication table for mod 2 is just like the corner of that. And it doesn't give us that much data. It tells us that odd times odd gets odd, otherwise we get an even. But if we're looking at a pattern like, can we get every type? Yeah. Is there any type that can't lead to another type? Well, evens can't lead to odds. That's a little data, but we kind of already know that. And the diagonal, which I've talked about a bunch, which is important by being what's known as the quadratic residues of that mod on the multiplication table. And there are other ways to define a quadratic residue, but I like the visualization of it being the diagonal of a mod table. Tells us what square numbers can be in that mod. So like, if I want to know what can n squared be, well, n can be, for assuming n's an integer, one of these types, and the square could be that type times itself or that type times itself. And so n squared in mod 2 can be either even or odd. There are both even squares and odd squares. Not that much data. But check this out. This is arguably where the majority of... There's a lot of number theory congruences, or meaning like relationships that hold true, sort of like a equation, but using this triple bar equal, meaning congruent to. So there's a lot of congruences that relate to mod 4. And a few of them, of the really cool ones, stem from this neat fact about it. That if I look at the quadratic residues of the smaller mods, mod 2, square numbers could be 0 or 1. It was both of the possibilities. If I look at the quadratic residues mod 3, we noted that 0 times 0 was 0, 1 times 1 is 1, but 2 times 2 got us back to 1 in mod 3. So really square numbers could only be 0 or 1 in mod 3 also. That did give us a clue. Square numbers cannot be pre-threeven odds. And that's why I was saying that mod 3 has some patterns that it's the first to expose. Although mod 2 is the first functional mod of sorts, mod 3 is the first that gives us data about the squares, really. But mod 4 is even neater, because if you look at mod 4, the diagonals still only zeros and ones. Now, in mod 4, having only zeros and ones out of 4 possible values is even a better rate. In mod 3, 1/3 of types of number couldn't be square. But in this mod, half of types of number can't be square. So you'd think, maybe there's some patterns to look at in that. It already tells me that square numbers, when we talk about a square number, we mean the square of some integer, and whether you squared a negative or positive integer, your square number will end up positive. So 0 is considered a square number, but funny enough, it's considered the 0th square number. And I kind of like when they do that, because it sort of gives you the option of including 0 on certain lists or not. Like, it's also the 0th triangular number. And then so it's like, it is one of them, but often you start the list from the first term. But in this case, we do want to start from including 0 and noting 0 fits that pattern. 0 squared is, doubly even. 1 squared is that. 2 squared's back to doubly even. 3 squared's back to that. The ones I was calling the early odds. So square numbers cannot be singly even. They also cannot be the late type of odd, the type of odd that's congruent to 3 mod 4. We could prove that also with this. You could square some of these things. We could say that all of the possibilities are 4K, 4K plus 1, 4K plus 2, or 4K plus 3. And if you square all of those and simplify it, you'll see that everything breaks down into bigger multiples of 4, except for 1 sometimes, and at other times it's just multiples of 4. So that's one of the neatest types of quadratic residues in the early lower mods. There are other ones that have really good ratios too of how many square numbers are included in the mod as possibilities. But in mod 4, we get a really great one. Only half of the congruence classes can be square. Now, there's a really cool thing that comes out of this. Now, this is based on something that was a theorem by Fermat, the great mathematician Fermat, many know from Fermat's last theorem. Well, a different theorem that he made was Fermat's last theorem he did not prove. I'm not positive on the status of to what degree fully he proved this other theorem, but it's called often Fermat's theorem of sums of two squares, or Fermat's theorem of two squares, or things like that. Different from many other similar sounding ones Fermat did of theorems, because he had a bunch. But this particular one says that for odd primes, it turns out in that definition, all odd primes are precisely the type of numbers that can be made, or odd primes that can be made from this as the sum of two squares, which can be seen geometrically as if I have a right triangle and these two sides are integers, any integer for these sides, whole number, then what integers could the diagonal be? And not even what integers could the diagonal be, but we have a squared plus b squared equals c squared. So like if I have 3, 4, 5 there, that tells me that the number 25 can be made as the sum of two squares, because that's 5 squared. So in this case, 25 can be made as the sum of two squares, 3 squared plus 4 squared. And the theorem says that for an odd prime, it'll do that if and only if it's the type that's an early prime and not a late prime. And there's a hard part to prove about that, which is that if you're an odd prime, you must be able to be the sum of two squares. But we can right now demonstrate the other easier half of it, which is that the ones that are the late odd ones, congruent to 3 mod 4, cannot be the sum of two squares. So right now we're not going to prove that all of the ones that say 1 mod 4 that are prime can do it. That's the harder part of the proof. But we can right now demonstrate super easy from this table the other half, that the 3s can't do it. How can we show that a number congruent to 3 mod 4 can't be the sum of two squares? Well, we said all square numbers are congruent to 0 or 1 in this mod. Because whether I was squaring one of these or one of these, they all end up in this mod simplifying to one of those. So the possibilities I could have for adding up my square numbers are, I have a pair of zeros, I have a pair of 1s, or I have one of each. Doesn't matter which order, 1 plus 0 or 0 plus 1. So if I add up two square numbers that were doubly even, I get another doubly even. If I add up two square numbers that were singly even, that's the addition table here. 1 plus 1 gets me 2 on the addition table. So if I add up 1 plus 1, that's congruent to 2 now. Meaning if I add up a singly even and a if I add up a congruent to 1, the early type of odds, one of each of those, then I get a singly even. Now if I add up a congruent to 1 and a congruent to 0, I get another congruent to 1. These were all the possible ways I could add two square numbers in Mod 4. So these are all the possible sums of two square numbers in Mod 4. 0, 1, and 2. Notice anything missing? 3. 3 is missing. You cannot make 3 by adding a pair of zeros, ones, or one of each. So when adding two squares Mod 4, you'll never get something congruent to 3. And so that's the easier half of that Fermat proof, which is that the only possible numbers that could be the sum of two squares, these are even, so the only possible odd numbers that can be the sum of two squares are congruent to 1. The harder half of the theorem is that then if you are a prime odd number congruent to 1, then you definitely can be the sum of two squares. So that's the part maybe we'll do in a future episode. But for those interesting, you could say look up Fermat's theorem about the sum of two squares. So, to all that enjoyed this, remember these deep concepts will probably come back in main channel episodes on the combo class channel, where I end up doing more polished versions of my thought processes and lessons. And when we do that, we'll not only have neater tables, but I will build a little clock for different mods. At some point throughout grade -2, I will be building little clocks that have 0 on top and a certain amount of hours, so that for a Mod 4 clock, for example, we can have 0, 1, 2, and 3 as the hours, and we can turn this into clock analogies. So, this will show up at some point way in the future as clocks. I had to go over it today, though, because it's one of the neater patterns out of many patterns that Mod 4 happens to have. There are a bunch of neat congruences related to Mod 4 in number theory, and we're definitely going to have to make a Mod 4 clock for that reason. I might even dedicate a stretch of wall in my room or in the background here somewhere to write down the multiplication mod tables permanently, not just on a whiteboard, like write them on the fence or something, because these things are going to keep coming back. Now, I'm going to answer some comments now, and that was the main focus of this stream. So we're going to wrap up after I do some comments, because I had to set up some stuff earlier. I was going to film the next part of my answers video to the final exam, but I need to finish filming that and get that good. So after this stream, I'm going to be filming a bonus video that'll come out later today. That is me going through the stretch of questions on that optional final exam I made that are related to different bases. So, for example, real quick, just to read the questions to you folks, the ones we're going to go over is about how many zeros are in the largest prime number known to humanity if it was written in binary? How are 3 different numbers written in base -5 without, or no, wait, how would you write the number -5 in these 3 different bases without needing a minus sign? How many zeros in base 12 would the following numbers end in? How many minimal pandigital numbers, as I call a type of number, are there in base 6? In base 9, what are the possible last digits of square numbers? And that's going to be similar to if I had asked in base 4, the answer would be 0 and 1. And in base 10, what's a 9-digit number whose 4th power is palindromic? Those are the questions I'm going to answer in that bonus video. Not just the answers, but also the logic you could use to solve them. So, now going through some questions. Thank you all for commenting. Also, yeah, earlier, I guess, Josh Hamilton also guessed about the congruent to 2 mod 4 for the singly even, and Mathematique Morse guessed the phrasing of 4k plus 2. I actually like the mod phrasing most. I like this, congruent to 2 mod 4. However, when you're doing algebraic proofs, sometimes it helps to double check them by running it through this way, like squaring that and stuff. It's a good way of coming to the same conclusion different ways. Someone's wondering what drives me to do math. Well, I very much like making videos that teach people interesting things, and I originally intended combo class to be a mix, more balanced of math, science, language, history, things like that, presented in my different way because I don't agree with all the way things are taught in schools and textbooks, and so at certain points I want to show my version of ways of learning certain types of language and history and things like that. But when I was planning grade -1, I found that for a few reasons, I ended up making the largest amount of math episodes, a trend that will most likely continue in future grades. There's a chance some future grades will have more balances of more science and language and stuff in between, but they probably will be pretty math heavy. A few reasons for that. One was mostly in grade -1. A trait was when I started this grade, I only had any money to put in the show coming from my own personal private music lessons I was teaching. And I was getting surgeries at the same time, so I wasn't able to work full time. So it was really hard to fund anything. And the easiest to film was me setting up a bunch of whiteboards full of math stuff in my own time back here in my own little backyard corner, and then hiring a camera person for just like 2 hours with all these whiteboards set up to like film an episode in 2 hours. And so that was what I could do. I also couldn't move places. Part of the finale episode that's coming out, it might be the last day of March because it's pretty long and dense to edit, but it's going to be coming out in March on the main Combo Class channel, goes into when I was making this grade, I was getting 2 surgeries and I couldn't go on what I call field trips to fund other places outside this classroom. We're going to do more field trips in grade -2 because I can walk again normal. And so part of that process is in the finale, some flashbacks and a field trip that I took this month, and the camping trip and such. But now I have more chance to go other places. There might be more episodes about animals and plants and all sorts of stuff I like. But the math ones were easier to do back here. However, that's not the only reason. It was also because while I was stuck here recovering, I spent a huge amount of time re-embracing my old mathematical side, reading a ton of used books about math, looking up things online, combing through a ton of online articles and stuff, making my own notes, exploring my own formulas, falling asleep thinking about different sequences. And so I ended up realizing I really enjoy numbers. I have a lot of fun with them. And so in particular, I got very hooked this grade on number theory, which is based on just whole numbers. Just what patterns do integers have? And really technically you could say, for given equations, what are the integer solutions to them? Or sometimes looking at the rational solutions to them. But you can also phrase them in very fun nicknames and simple expressions, like how one of the big open questions in number theory is the twin prime conjecture, which you could phrase in a very technical way, but you can also just say it means, are there an infinite amount of primes on consecutive odd numbers? So there's a lot of stuff about number theory I fell in love with, and there's tons more of that that's in my notebook that I didn't end up putting in this grade. So for sure the next couple grades, if not all the grades, are going to be pretty math heavy as well. Other things will depend on when I have cool visual stuff to accompany it. Like I want to do science experiments for real in the episode. I need a way to actually have weird gear and stuff like that. I'm getting closer to have more options due to a mix of my physical leg health and getting some funds from Patreon and from YouTube ads. So I still spend, it's maybe at the point where I make as much as I spend on Combo Class, so I haven't made any money like for me to spend or anything. I still live at home. It's not at the point where I can move out yet or anything. I invest all my money in it, but it is at the point where I'm starting to get a little more of a budget that lets me have the opportunity to like hire an animator for a scene or like take a field trip somewhere that costs a little money or stuff like that. So we'll have a little bit more of cool stuff in grade -2 because I am going to invest all my money into the show, and there are people supporting on Patreon and stuff. So someone's mentioning they think it looks good, and there will be fans of both looks. The hair will need trimming up. I'm going to have a friend tidy up the hair because I did it myself, like literally just while being filmed, like not looking at it in a mirror or anything. Then in a mirror later, I cut off like one or two extra scraggly things, but it's pretty much just me not looking at anything, cutting it with scissors. And so I would say I did surprisingly well. You'll see the scene of me cutting it in the finale, and as well as the scene of when I shaved the first half. And for the entire finale episode, between the beginning and end, I have the half beard because it was filmed over the last week or two and I had that. And fans of this look will like the earlier grades probably. Fans of the chaos hair will probably like the later grades more. So we're going to see both sides of the cycle and everything in between. So better get used to changes and evolutions. But they will change and evolve sometimes in similar ways. Like, for example, I will be setting up another desk back here. And I will probably be letting the elements, interact with it in a way that will probably make the desk break again at some point in the grade. Will probably be a point where my new lab coat gets that stained. So, go through some seasonal arcs. Now, also to remember, with any weird thing I do with my looks or my set or whatever, the streams are my behind-the-scene playground, but I mostly do all the planning of when I do what with my face, my hair, my set, based on the main channel episodes on the Combo Class channel, which I see to a degree like a TV show that I don't only want to make math. I also like to put running gags in it, little bits of lore, little evolutions and little clues and stuff. And so usually if you see something change in the stream, it's sort of like a behind the scenes of something I planned for the current season of a TV show that I'm crafting or whatever. And so when I say like this is the finale episode coming out, it's sort of like a season finale of a TV show. Although the finale episode that I'm putting out this week is going to be more like a little documentary film. So I hope that a bunch of you will consider, spending some time within the week or two after it drops before the grade -2 intro hits, which will be maybe a week or two after the finale. In the finale, try and sit down sometime and really watch through all like 45 minutes or maybe an hour, whatever it gets edited down to, because it means a lot to me. It's the longest project, not counting live streams, the longest like edited project that I will have ever released in my life. And I've released many things in my life. I've released dozens of musical albums. I've had many YouTube channels. There's many things you guys don't know about. Some of them are flashbacked in this, others are saved for later. But this will be the longest thing I think that I will have released of a edited film project. And someone's asking how old I am. I'm 29. I'm not that far from 30. I'm not going to say my exact birthday here, but at some point during this year, 2023, I will be turning 30. And right now I'm 29 for a bit. So the funny thing is, some people say I look younger than that when I have this shave, and some people say, or they probably don't say out loud, but think I look older than that when I have like really underslept, really long hair and stuff. I'm still pretty in the underslept mode. We'll get a little freshened up by the time grade -2 hits. But yeah, I am 29. So, but it is funny because I do see parts of my personality as being quite childish. I enjoy playing with bubbles. I enjoy, like look at, oh my God, a squirrel, and like little things like that. And another part of me to be relatively wise, because I've been through a lot of things over these 29 years, including a time where I almost died, and I had to spend like a year recovering from almost dying about 2.5 years, a little under 2.5 years ago. And so yeah, there's ways in which I'm very wise, and there's ways in which I'm purposefully retain my childish curiosity. Someone's asking why they got an F then. Well, even if you watch all my videos, they might not line up with your class's study material. As I've said, what your class might make you study, depending on the teacher, might be heavily memorization based, might be repetitive, might not be the stuff I like to teach. The stuff I teach is sort of almost purposefully the stuff that gets left out of school. So I wouldn't say that any of my current things are a good study guide for a given high school or college class or middle school class or whatever. Maybe someday I'll do that, but right now my videos are things I find beautiful about math that are often not taught in schools, at least not as soon as they should be, or not in as general of a field as they should be. So don't treat my stuff as something that will necessarily help you pass school. Treat my stuff as something that will make you what I consider to be smarter, wiser, and more appreciative and more knowledgeable and such. So that doesn't always line up with what schools think those mean. Some teachers are great though, so do try and respect your teacher, try and get what they're offering. Sometimes it won't be great and you just have to fake it till you make it and study it and forget it. The stuff I teach, I like to have be things that aren't just like memorize this, then forget it. It's like, if this is a useful enough tool that you need to memorize, don't worry, it'll show up in more episodes in the future in clear detail. And none of my stuff so far has been like, here is a tutorial on how to survive this aspect of the world. It's really just about knowledge and appreciation. Maybe at some point I will make tutorials of how to go camping and such. Like we got a camping tent here. But, you know, so far the grade's about knowledge and appreciation. So, someone's saying in mod 10, any multiple of 9, the digits always add to 9. And is this true with other mods? Yes, so in fact, many of you may not have seen because it was right at the beginning, the first math episode that I put out on the main combo class channel, not the intro episode where I set up some clocks in my desk and put on my lab coat and unwrap the whiteboard. That was an intro episode that I put out last May, and right after that, the next episode is called Something About Nines. And in fact, I don't want to go all the way around right now, but I have a 9 spray painted on the side of my house that now I have decided, since I'm extra in love with the number 6 these days, it's an upside down 6, we're going to call it. But it's a 9 or an upside down 6 is spray painted on the side of my house. That's in the episode. In that episode, I go into how, yes, in a base such as those in a base B, the number B minus 1 will have very cool divisibility traits. And as for when I found maths interesting, probably to a degree my whole life. I've always been curious about different things, and numbers have cool patterns. So I liked playing around with numbers a bunch when I was younger, and then I got super reinvigorated when I was stuck at home recovering from not the 2 surgeries I got last year, but before that when I broke my femur, the biggest bone in your body, and a lot of ordeals to tell you guys about someday. But I was stuck at home for a while. I ordered a big stack of used math books online, and I was reading through a giant stack of used math books and reinvigorated my love for math that I have at times gone back and forth in life between my more mathematical, logical side and the side of me that's a little more creative or even spiritual, that appreciates nature or making music or other forms of art, writing fiction, things like that. So I have a sort of clash to balance in my personality of when I guide myself toward the mathematical objective side or when I guide myself toward the more creative subjective side. And in combo class, it's a little more toward the mathy side, but I like to put a mix where we also, you know, appreciate things that we're not trying to attach a number to right now, that we're just seeing other forms of pattern. But I've gone back and forth and got really reinvigorated in liking numbers after many phases of liking them throughout my life. Really reinvigorated like 2 years ago when I was recovering at home from that stuff. And since then, I have been sort of fully in that phase where I spend a decent amount of time, some amount of time each day, writing down notes about playing around with numbers and trying to find patterns. And thank you to all of the other nice comments. So I'm going to wrap up the stream in not too long, but we can take a little glimpse at the combo classroom first. Now, to actually see the full status of these things, you're gonna have to wait until that finale episode, which I'm gonna be spending like all week editing because I have it cut down to an hour so far, but there's a bunch more cutting, both adding stuff and subtracting stuff I have to do. So it's gonna be somewhere between 40 and 70 minutes. I'm not sure exactly, but it's a whole documentary I'm crafting. I haven't even started on like the audio levels or anything. And so that's going to be my week because I said on the main channel in the test episode that it's coming out in March. And I'm going to make that happen. So it's probably going to be coming out right near the end of March so I can make sure it's as good as I can make it. But that will explain a lot of things here. But we're just going to take a really quick tour. And you folks can decide what sort of clues you want to look for. Also, I forgot to wear these in the finale. I need to wear these more, these hexagonal sunglasses. So, 6s will definitely return, including hexagons, in this next grade. A few things, by the way, if you want to know a few math concepts that I know will come up in this grade in a recurring fashion, is be on the lookout for triangular numbers and square numbers. Be on the lookout for modular arithmetic patterns like these things. And be on the lookout for more 3-even numbers. And there's not an episode yet as to this comment who asked, is there an episode about why integer powers of the golden ratio get closer and closer to an integer? There's not, because every time I start deciding maybe it's time to film an episode about the golden ratio and the Fibonacci sequence, which we got some of the patterns of it in the episode about fractional and irrational bases. That goes into the golden ratio base. So some of the cool patterns are mentioned there, but it doesn't go into that pattern you mentioned. That pattern, among many other patterns I want to note, is in my notes in my combo class documents, that there's so many cool patterns about the golden ratio, and I have a whole book I've got when I was really young about it. I discovered the golden ratio, not like I was the first to discover, but I stumbled into it myself as a kid, and then later I found it again. I'm like, oh my god, it's that number. And I'll tell the story about that in the episode for sure. I might even revisit the place where I was when it first came to me when I was fiddling around and found it. But I haven't gone into that because there's so many cool facts about the golden ratio and the Fibonacci sequence that's actually related to that fact. And the Luca numbers, often called the Lucas numbers, but his name probably would have been pronounced more like Luca. And so the Luca numbers and the Fibonacci numbers and the golden ratio will be probably a few episodes because I wasn't able to ever fit all my notes into just one thing. There were so many fun facts I wanted to put. So we got little hints about the golden ratio in a few things. The next time we're going to see the golden ratio will probably be an episode about how and why the golden ratio can be said to be the most irrational number, which is a weird thing to try and assign to a number, but you can argue that it is. And there's also a thing that we'll go into there called the irrationality measure of irrational numbers. Now, there's various ways to try and measure that, but that may be the next time we go into it. As far as that fact, I'm not sure when it'll show up, but it will at some point. And whoever asked me to help them solve their examination hall questions, I'm sorry. I purposefully quit doing private lessons, even though now I stopped making money from it, to focus on being able to make content for many people to learn from. So, I'm sorry, but it's very unlikely that I will do free tutoring after just having quit paid tutoring. But any questions that you are curious about, you can feel to ask if you think that it will start a good conversation, if it's less like solve for X here. So, someone mentioned that the golden ratio's continued fraction is all ones, and yes, that is very linked to its irrationality, that it's harder to approximate at each phase. Turns out that when you see a large denominator in this thing called the simple continued fraction, it means if you cut it off right after that, you get a good approximation. And in pi, there's this continued fraction way of writing it that has a 292 somewhere in it. And if you cut it off right after there, you get a pretty good approximation. So someone's asking a viral question about PEMDAS. What is my answer to this equation? My answer is that it is ambiguously written on purpose to try and spark debates. And I actually am going to make a video at some point about how I think those questions are pretty silly. They're meant to get comments because comments help in the algorithm. They know it's going to spark a debate, but it's really just a semantics issue. Semantics meaning like the way you're using the language. Where if you were writing that in a mathematical equation, a mathematician would either put another set of parentheses to clarify or would write the fraction as a bar so you know what parts are over what. And so all of those questions are written ambiguously in a way that a mathematician would just not write it that ambiguously. And so there's no real reason to come up with some crazy, this is the correct order of operations. People thinking something is the permanent correct way is actually a little short-sighted because it shows they're not aware that things change rapidly through history and that things are currently different in different areas of the world. So it's, not very aware of the current world or the past to think that there's a correct way to interpret that. The goal of writing down an equation is for it to be understandable, and that could have been written in a more understandable way. So that's my opinion on that, which I will make more thoroughly in an episode where we go into how there are many questions like that that are purposefully written where the division could go before or after something. So those questions are funny. Someone's saying, have I heard of the Einstein tile? I'm not sure. Let me look that up real quick to refresh my memory. And it's noting a 13-sided shape that can tile things. No, I should read more into that. Sounds pretty cool. It says that it is a aperiodic monotile. So, yeah, those are shapes that can tile a plane without mapping, and what this is reminding me of is what's called Penrose tiling. We haven't done that in an episode yet, but I'll look more into that. Maybe that'll show up in an episode if we do one about those topics someday. All right. And another funny thing about those math equations is that people have this weird interpretation of math that if you have a really long, hard equation and you can solve that, that makes you a mathematician. And if you can't solve the really long, hard equation, you're not a mathematician. It's not really how it works. Mathematicians don't really spend their days like, okay, I solved this equation. Time to solve the next equation. Time to solve the next equation. That's like when they're in school, they do that. When you're actually like, if you're a research mathematician, then you have the, you need a lot of creativity. You need to think about, how can I link this to that? What can I try next? What would this do? And so it's kind of funny when people have those questions accompanied with like, only 99% can solve this, and those are the geniuses. Well, even if those were true, if there was like a really hard but not ambiguous question that 1% of people can solve, it would not necessarily be the mathematicians who are good at solving that, because mathematics often requires, I'm more of like a math teacher or a math creator, but a research mathematician often has to tunnel into a certain field pretty deeply. And if you ask them about a random like algebra question, they might be like, what are you talking about? I've been studying topology. I don't know how to solve that long series of exponents and limits. So Remember that mathematics takes more creativity than some people give it credit for. And if you're good at it, it doesn't mean you're good at solving long algebraic equations necessarily. And I someone's mentioning those Einstein tiles were proved just a few days ago. That sounds really cool. I'll look into that. I think it's probably related to the Penrose tiling with different restrictions or dimensions. And that's cool. I will definitely look into that and consider working that into some sort of video. And let's see. I think I'm going to wrap up the stream in a moment because although we got a bunch of awesome combo lords here leaving cool thoughts, I want to film that answer video where I'm going to go through the answers to 6 questions about bases on the final exam. And that will have some things to do with our doubly even mod charts we made to a degree. It will have some patterns in common if we'd been playing around with slightly higher mods. I didn't ask about mod 4 in that one. But that'll be a fun video. I'm going to need to film it and then upload it. So that'll be out sometime later today. And then I'm going to be editing that finale episode. So other things coming this week will be the third and final part of the test answers will be coming tomorrow or Wednesday. There will be another stream on Thursday that I do in the evenings here. And either Thursday or Friday, that finale will be dropping. And as for one last question, somebody asked if I play video games. And I don't really. I actually, like I mentioned once in a stream a while ago, I like imagining game design, such as designing maps or puzzles or inventory things. So I actually like thinking through designing puzzles in games and stuff, but I'm not really a fan of technology in general. I don't really like video gaming as a hobby. I had some games I liked for fun as a kid, so there's some that would definitely give me a good nostalgic vibe, but it's not really one of my main hobbies. So, thank you all for joining me. Hope you all have a marvelous day. For our little peek I promised at the classroom, we got a little tent down there that I will need to be removing before it rains again. We got our staghorn fern, a quite burnt lab coat, and maybe a few more clocks than before. But that's just the start, because not only is there way more stuff in the finale than showing there, but there's stuff I didn't put in the finale that will be in the grade -2 intro. I have gotten some really cool things for the classroom for grade -2. There's one thing in particular that I have not mentioned on a stream, even though I really want to, because it'll be way more fun as a surprise. But there's something really cool I got for the classroom. So, I am from America, to the viewer from India who asked. I am from California in America. And we're going to wrap up here. So thank you all for joining me. Stay tuned for probably the amount of time to film it, upload it, and process it will be 2 or 3 hours. So in 2 or 3 hours, there will be a video on here going through some questions about other bases. That's the answers of questions 6 through 11 of my final exam. And somebody asked if I've explored magic squares. I have not yet. Highly recommend the Mathologer video that came out recently about those. The channel Mathologer is probably my favorite math channel. It's hard to put one above 3 Blue, 1 Brown, but I think I would put Mathologer even higher. And his newest video, the guy who makes it, Burkhard, is about magic squares. In fact, there's this one in there called Geomagic Squares that are geometric magic squares that are really cool. So, definitely check that out. Magic squares will show up at some point. So, catch you all later. Make sure to watch that answer video unless you are thinking of doing the final exam yourself, in which case, just rewatch or watch the main Combo Class channel latest episode about the test if you think you might try it yourself. Otherwise, it will definitely help out. And somebody mentioned Mathologer, I think, right after I mentioned that, because we have a slight delay. So good recommendation. Great videos on all of his videos. So I'll catch you all in the next one. Thank you for joining me. I'll have that video up in a few hours. And most importantly, make sure that at the end of this month, you dedicate an hour to watching my documentary finale. That's on the main combo class channel. All right. I love you all so much. Thank you. And